So if I have a very thick accent and you might have trouble hearing me or you might have trouble understanding me, I'm sure you will. That's fine. Come talk to me at the booth. I'm happy to talk about this thing for hours and hours and hours. Okay, so I work on Atlassian Marketplace, as we just pointed out. Atlassian Marketplace is looks like this. This is a screenshot of Atlassian Marketplace. It's a place. Everyone here is well, a big percentage of you are probably developers, being a developer conference. So this is a place that you can go to if you make some sort of add-on or extension to any of our Atlassian products. You can come and upload it here. So this is what I work on. It's made up of about 100,000 lines of purely functional Scala code. So this whole application is just a function. So I've got a lot of experience in doing this, and I've got a team here in Bangalore that is only writing functions to implement this web application. Okay, so I don't want to go too much into how we achieve this. I just want to go into some of the things of like what happens once you have achieved this, what comes out of this as an outcome. So I just want to kind of have a look at the definition of functional programming. It's just programming with mathematical functions. So something that takes an input to an output. That's all that we write on this Atlassian Marketplace. We only write functions that take input straight to output. That's the only thing that we do. Okay, so yes, I want to focus on just the consequences. I don't want to go too much into how we achieve this. I just want to tell you about once we have achieved this, once we write functions that go from input to output, what do we get? What's some interesting things that we get? So I want to go through a couple of topics like was mentioned. So there's something called equational reasoning. We're going to start off there. Then we're going to go through to algebraic types and algebraic laws. There's a little bit of relation there, not too much. They're kind of separate. So there's property-based testing as well. I want everyone here to do property-based testing after this. And then we'll finish off with my favorite topic, which is parametricity. Okay, so equational reasoning is the implication, once we have the idea that equality means, when we have the equal sign in our programs, once we say that means equal and not, assignment, then we get this benefit. So there's the idea of referential transparency. So this is a property of expressions. If once we have an expression in our program, we can talk about whether it's a referentially transparent expression. And so, it's the ability of being able to take an expression and assign it to a variable without your program changing. So everywhere you see like an expression in your program, if you've got the same expression, you can assign it to a variable and your program should not change in meaning. It might change a little bit in performance, but it won't change in meaning. You'll get the same result. And also you can do the opposite. If anywhere you've got a variable, you can just inline it. If you can always do that, that's functional programming. Okay, here's an example. Here we have hello.length multiplied by hello.length. So those two cases where we have hello.length, we can assign that to x, and we can say x equals hello.length, and we can say x multiplied by x. And this is the same program, right? This is 25. Everyone agrees that this is 25? If I counted them, there's 5 characters in hello? Yes. So it should be 25. Okay, so the program didn't change by us assigning it to a variable. Now there's another example down the bottom, and if you have done some Java or you've done something similar to Java, you might see that read line. If you do a read line and you do a length on the read line, every time you execute that, it's going to go and read from the console. So here, if we do readline.length and you multiply that by readline.length, different programs. Everyone agree that if you were to assign this to x, you'd have readline just happen once, whereas if you have readline.length multiplied by readline.length, it's going to read it twice, right? So this readline.length is not reference transparent. So in functional programming, we only use this reference transparent expression. Everything we write is reference transparent. That gives us some benefits. For example, we can do this thing called equational reasoning, where any time I've got a function and I want to understand what it means, I can just start substituting. So everything is just substitution. So here I have like f of x equals x multiplied by 2 plus 1. So if I had an expression that was f of 0, I can actually just expand out the definition. So I can just start inlining the definition. So here I've got x multiplied by 2 plus 1. So if I substitute 0 in there, then I can start evaluating it. So I can say that f of 0 is obviously equal to 0 multiplied by 2 plus 1. This is always true no matter what functional programming, no matter what function you have when you're doing functional programming, this is always true. And so then we can look at the definition of multiplication. So 0 multiplied by something is 0. So then we have 0 plus 1. Then we can look at the definition of plus and say 0 plus anything is anything, right? So we can substitute it out. So in my head, I can evaluate this program. I don't have to understand, memory model or anything like that. I've just got this. Very, very simple way of simplifying code or understanding how code works. Now here's another one. This is quite a complicated thing. I understand what this code does, but I'm sure a lot of people here don't understand this code. So there's something called traverse underscore. It's a common function when you're writing something like Haskell or Scala. This comes up a little bit. Let's understand what it does by using this equational reasoning. So we can use the equation of traverse. So traverse equals a fold right, fold R of something. And then we can use the equation of fold right. So we can look at the definitions and we can start expanding it out. So our original program, which looked like traverse of underscore of this printing hello and then printing world, we can start substituting out the definition. So we've got this fold R, so we can expand out fold R here. And so now we've substituted out, now we've got no occurrence of traverse underscore. So this bottom, we can substitute it out and have this program. So we can say that the original program is equal to this new program. Then we can go another step and we can expand out fold right. And so now you can see we've got a printing of hello, and then we've got this asterisk greater than thing, so there's some sort of symbol there. We don't have to fully understand this code, we're just trying to simplify it a little bit. So we've got another fold right, we can expand out the fold right, and then we've got yet another fold right, we can expand that out, and we can end up with this. So we have printing hello, and then we've got this operator, and then we've got printing world, and then we've got an operator, and then we've got this pure unit thing. So what we're saying is that this traverse underscore of this original program is equal to this second program. So just by kind of expanding out the definitions, we're able to say that these two programs are equal. Now this might not tell you much, it might tell you not, you still probably won't understand the bottom program and you won't understand the top program, but we know that these are equal now. And now I can talk to my team and say, okay, let's start talking about this operator. What does this operator do? And then we can figure out what the code does. So just by kind of iterating and using the definitions, we can step through the program and figure out what programs are equal to each other. Really cool property. Now, algebraic types. So it's a way of building up and breaking down data. So there's the idea of the cardinality of a type. So you can view types as some sort of mathematical set, and you can view values inside of that type as inhabitants, or as some sort of you can count how many possible values are inside of this set. And so, for example, there's infinite strings, right? You can keep coming up with strings. There's 2 to the power 32 integers. There's 2 booleans, for example, and so on. So there's like a count of how many values are possible for a particular type. Now, there's the idea of a product type, which is if we were to take these kind of primitive types that we have, we can combine them together. And one example would be like this review type here. So we have a review type, and we can combine together this review ID, which is just an integer, and then we can combine together with date time. And then what we have is the cardinality of this data type being the multiplication of the cardinality of each of those underlying types. So we have an int and we have a long. We can count the cardinality of each, and then we can multiply that together. And that's the cardinality of review ID. So we call this a product type, because what we're doing is we're combining these things together, and to count how many values, we just multiply them together. Does that make some sense? Now there's the opposite, which is a sum type. So instead of multiplying together or combining these fields together, we can say that this set contains this value, or it contains this value. And one example from our code is an environment. So we have local environments, we have staging environments, we've got production environments, and we have dev environments. But we've actually got, in actual terms, we actually only have 30 dev environments, but we represent it using an int. So we say that there's 2 to the power 32 possible dev environments. We don't use all of them. We don't have that many developers. We've only got a couple, so we have about 30 of them. But what we can do is just count up the inhabitants by adding together these possible values. So there's local, staging, production, so that's 3 of them. And then we've got 2 to the power 32 possible dev environments. So it's 2 to the power 32 plus 3 possible values for this. So that's why we call it a sum type. Okay, now sum types, you can see here, this is a bit of syntax. You can see that there's this operator here that's combining together combining together the possibilities. So this is something that's built into Haskell. Scala's got some sort of support for it. But a lot of tools, I think Java's getting some sort of support for this soon. It's getting case pattern matching in Java 12 or something like that. But you might be using a tool that doesn't currently have that. So we can use this thing called Scott encoding or church encoding. Scott encoding and church encoding are a little bit different. I can tell you about the differences. There's an interesting difference, but for this it won't matter. But we can use this technique to write these sum types in a language that doesn't really have built-in support for it. So what we do is we write a visitor. This is a little bit different from the gang of 4 visitor pattern. The gang of 4 visitor pattern usually has, down the left-hand side here, instead of having a, it has void. Our version, we don't use void, because we do functional programming. We always return something, so we don't return void, we return a. So this is a little bit of a different take on the visitor pattern, but it's basically just representing it as a visitor. The underlying mathematical concept is called a polymorphism or a fold. We won't go into that, but if you're interested, you can Google that. So once we have a visitor, then we can actually implement our data type. So here I've implemented the local. So this is the case for local. And so what we do is we just visit that local. So we just call that visitor with the local. And then to actually write functions in terms of this, we can actually just implement a visitor. So here we're writing a visitor that will return a string. So here for local, it'll return the string local. For dev, it will return the string dev dash whatever count it is, whatever index it is. And you can do that for staging and prod. So this is just a way of kind of taking a data type, a sum type that has multiple different possibilities and encoding it using a visitor pattern, which might be useful to whatever tool you use. So we use this when we have to write JavaScript in Java. So we've got 100,000 lines of Scala code. We've also got a little bit of Java that we maintain. And so when we have to write Java or JavaScript, we use this encoding to take data types that are sum types and encode it in Java. Okay. So algebraic laws. So this is about talking about when or what should be equal to each other. So there's the idea of a monoid. This is probably the most popular algebraic data type that people are familiar with. So a monoid is something that's a binary. It's an associative binary operation. And so associative means that it doesn't matter where the parentheses are. If you've got A and B and C and you're using this operation between each one of those, it doesn't matter if the parentheses are on the left or on the right. It doesn't matter which one you evaluate first. It's the same program. And also you've got the identity element. And so if you've got the identity element on either side of the operation, you don't have to do the operation. It's the same thing as not doing it at all. So this is a monoid. And we use this all over the code. This is very, very common in our code base. Here's some examples. So there's addition with 0 is a monoid. There's multiplication with 1, which is a monoid. And then there's string concatenation with the empty string. These are all four monoids. There's also lots of monoids that we actually implement in our code base as well. And we use this a lot. But there's also laws that we come up with. So we came up with a law which is, if you create a user, then you can find the user after you've created it. That seems like a pretty straightforward law, right? There's also the idea of updating. So you can create a user, you can update the user, and then you should be able to find the user that's been updated. It shouldn't return the original one, it should return an updated one. And we use this in our tests actually, so I'll talk about that in a minute. But the idea here is that we can write what we expect our API to uphold as a law. And this is useful for refactoring. You might have heard of MapReduce or something. So refactoring can be part of, if we take a program that works, we can make it faster by refactoring, and MapReduce is a way of doing that. It allows us, if you've got a monoid, MapReduce is very, very easy on a monoid. Also, but for simplification is kind of the main part here. If there is a law that I didn't mention before, but with our original program before where we did the traverse underscore, and we substituted out and we said traverse underscore equals this new program, there's a law that says that that pure of unit, if you do it with this, if you do it with that operator, it's the same thing as not doing it at all. So there's a law there, so we can actually simplify it even further than what we had before. And now I've just got this program. So I had traverse underscore of the original program equals this, which I think is really cool. So we've gone from something that's quite complicated, traverse underscore, to something that's quite simple. And the biggest thing that we get out of it though is reuse. Huge amount of reuse out of this. So these are different types of algebra. So you've got monad, functor, applicative, traversable, like all of these different types of things. And we just write lots and lots of functions in terms of these things. And we also get them for free. Other people have already written functions in terms of these algebras. And so we can just reuse it. So lots of code reuse. That's the main motivation there. We're able to go a lot faster because we're able to reuse code very quickly. Okay, so property-based testing. So once we have these laws, we can do something called property-based testing. And what we usually do when we do unit testing is come up with specific cases. So you might come up with a user, you might say that the username is Brian, and then you might say that the email is bmckenna@atlassian.com, and you come up with all of these fields and you start filling it in, and you have your test suite, and at the top you have like a user Brian, and then you go and write a test in terms of that, and you say the user Brian can be inserted, and I can find it, and it's Brian. What we can do instead is write it more generically. So here I've got a property-based test. And it means it's a property-based test because I'm not specifying to create Brian. I'm saying I can create a user and I can find it and it will be exactly the same user. So I'm saying just any user, doesn't matter, you pass me in a user, I can create it, I can find it, and it's going to be the same user. So I've written it as a function. I'm taking in a user rather than asserting a specific user. So I'm not being specific. Now the bottom there says, for all F, so these are going to be users, for all users, we can run this property. And so this test framework will go off and generate 100 different users and assert that this property holds. So instead of manually kind of constructing a user, this test framework would just throw in 100 different users for me. And the way that it generates it is through something called a generator, and it's a way of composing together different data types or different generators to combine up a bigger one. So here's a plugin description. So it's got like a summary string, it's got logos, optional logos, and so you write this generator and you write it once, and then you say run the tests with this generator. And so it'll go off and generate a heap of different values for you. By default, 100. So my test case, even though I've written it once, I've written it very straightforward. You know, you can create a user, you can find a user, generate 100 different versions. And some of those, sometimes it'll have like an empty, maybe empty name. Or maybe it'll have a name that's got 1 character in it, or maybe it's got 100 characters in it. Maybe I didn't consider that there will be a username with 100 characters in it, so that's something that I have to consider now. So it'll show that there's maybe invariants that I haven't thought about, or there's maybe cases that I would have thought are edge cases, but generated automatically for me. So I don't have to think too carefully about what needs to be passed in. I can just think about, you know, I need a user, and I can create a user, and I can find a user. So I can think about it in the abstract and test it out and see that my session holds. Okay, and then you might think that if you're generating, you know, usernames with 100 characters and you're generating groups with 100 groups, you know, it's going to be generating a massive data structure, and you've got an error there somewhere. You know, you'll get back an error message that says, hey, that probably didn't hold. And you'll be like, why didn't it hold? You know, I've got 100 groups in here, what's the problem here? So there's the idea of shrinking, which will, once it generates a bit of code or a value that doesn't succeed, it'll then try and shrink it back. So it'll try and reduce the parameters in it. So, you know, I might have a 1,000 character long username, and it'll start shrinking it and shrinking it down, trying to find the minimal use case or the minimal failing property. So really cool technique. We don't use this enough on my team, but we do use it a little bit, and when we do, it's very, very useful. We definitely need to use that more. Finally, parametricity, my favorite topic, definitely my favorite topic. So we can use polymorphism to our advantage, and we use this all day, every day on my team. So here's some functions. So the top two, there's only one implementation. So the top one is saying that if you give me an A, then I have to give you back an A. But I'm not specifying what that A is. I'm not saying that A is an integer. I'm not saying it's a Boolean. I'm saying you give me any A, I'll have to give you an A. And you get to determine what that A is. You get to tell me whether it's a string. You get to tell me whether it's an integer. And I have to return you back an A, whatever you chose. So I can't come up with an A. I can't just come up with an integer and say, there's your integer, because you might want a string. So in this case, the top one has only got one implementation, because if you give me an A, I have to give back exactly that A. There's no way for me to know what that A was going to be, so I have to return it. So this top one, there's only one implementation. For the second one, I'm saying if you give me an A and a B, I'm going to give you an A back. There's also only one implementation for that, and it's to ignore that B and to return that A. Now, there's the third one there, which is impossible. If you give me an A, I'll give you a B. But you get to choose what the B is, which doesn't make any sense. I can't just give you a random back B, right? If you say, I want a user, I can't just randomly give you back a user because I've only got an A. So know that this function's impossible. So this is something that comes up sometimes in our codebook, kind of make ourselves, like we'll try and implement something and we'll find out, oh, we don't have this data, we don't have the possibility of implementing this, and so we know that we've gone the wrong direction with something, or that we don't have enough data, so we'll have to pass it in, or something like that. So this comes up sometimes as well when we're implementing it. And the last one, reverse, there's actually infinite implementations for this one. We're dealing with a list of A's, and we're going to give back a list of A's. And I can do many different things with a list. If you give me a list, I can, say there's 100, I'm going to repeat that list 100 times, or I'm going to repeat it 42 times, or I'm going to repeat it 1,000 times. So I can come up with an infinite number of implementations for this. But there's some things I do know. One of the things I know is that every time I look at the output, every element that's in the output, because it's a list of A's, every A that's in that output is going to be in the input. I can't construct an A out of anything. I can only pass through A's. If you chose what the A is, if you said it was a string and I try and give back an integer, that's not going to compile. So I know that there's an infinite possibility of implementations here, but I know that there's certain implementations that are definitely ruled out. So even though it's infinite, it's less infinite than just anything. I can't just do anything, I can do a limited set of things. So this is useful as well. And this goes into the top one is actually more, if we can implement things generically, then we should. This top one is a lot more simple than the bottom one. The top function here has only got one implementation, whereas the bottom one has got 2 to the power 32 implementation, or 2 to the power 32, 2 to the power of 2 to the power 32. That's a lot of implementations. So the top one, 1. So it's definitely, if you can get away with using polymorphism, you should definitely try and use polymorphism. It directs you towards implementation. And here, similarly, there's like a list at the bottom, and lists, I can do things with lists, whereas at the top, if it's a functor, there's only one thing I can do. Functor's only got one method on it. So here there's just one implementation at the top there. So again, like if you use polymorphism to the advantage, you get to direct yourself towards implementation and rule out a lot of different implementations. And here's one from our actual code. We've got this function called unsubscribe. And it can do things with config, it can do things with users, and it can do things with notification settings. And those are the only three interfaces it's able to use, because we're defining in terms of this polymorphic M. So I don't know what the M is. All I know is that I can do user things, I can do config things, I can do notification setting things. So I know I'm not going to go and touch plugins. Like plugins is an idea inside of our application. I'm not going to do anything with plugins. I can't possibly do anything with plugins. This is written in a generic way that the only interfaces I have access to are these three. So once we do function program, we can restrict the implementation. So if I'm trying to find a bug in plugins, like there's a plugin that's getting randomly deleted, I can rule out this function. I don't have to look here. I think that's really interesting. And this leads into hole-driven development. Once we kind of restrict what we have access to, we can use this hole-driven development thing. So I can give someone like that unknown map. I said that there was one implementation for that. Let's derive it. So I know here, so this is using something called hole-driven development. In Haskell, we can put an underscore before something, and we get a really nice error message. And the error message will say something like, oh, you need to give back an f of b, and what you have in scope is, well, you've got an x, which has got a b, and you need to return back an, you need to return back an f of b, but you've got also a y, which is an f of a. So we have these two things in scope. So I can use these two things to kind of derive or to get towards this solution. So I know I have to return back an f of b, I have an f of a. I also know that functor, in my head I already know this, so I haven't put it on the screen, but there's something called fmap inside of functor. It's the only possible thing that we can do with this f. I just know that. So let's start off there. I can say that we can fmap on y. So I've taken a step there. I've used some of my information that I know in my head to kind of get us towards more of a solution. But I knew that we had to return an f of b, so that's useful. Now here I can say I need to do an fmap, but I don't know what to fmap with. I don't know this function that I need to pass in here. So I can put an underscore to do, and it will say you need to pass in, you need to replace that underscore to do with a value that has type of a to b. And so I can look here and what I had in scope. Okay, well let me create an a to b. So I've brought in this a. Now I've got these things in scope. I've got an x which has got type b, and look, I need to return a b. So you need to put a b here in this hole. This underscore to do, you need to replace it with a b. And if I look at what I've got in scope, I've got an x, which is a b. So I can just pass in x there. So I can use the error messages that I'm getting from the compiler to get toward a solution. So if I know that I need to return something, I can use these error messages to kind of get towards a solution and iteratively kind of put in these little holes and say, give me another error message that tells me what I need to put here and tell me what I have in scope so I can get towards that solution. So that's something my team does a lot. When we don't know how to implement something, we put in holes and we start figuring things out. Really useful. And finally, three theorems. We have the idea of like an algebraic law. So we have these algebraic laws. Free theorems give us these algebraic laws for free, as the name says. So if we have a polymorphic type, so if we use polymorphism, like the identity function we had, for all a, you've got a function that takes an a to give back an a. We get this property for free, so we can say that it doesn't matter what you put here. If you compose f with id, it doesn't matter if it's either way. It doesn't matter if you put id before or after. And we get this for free from the polymorphic type. Just by writing down the type as polymorphic, we get told this law. So I can actually ask the compiler, what algebraic laws does this function uphold, and it will tell me. Another one here is mapping and reverse. So I can say, what's the free theorem for reverse? And it says, well, it doesn't matter if you map first or you map afterwards. It doesn't matter. Reverse is so polymorphic that it doesn't matter whether you map first or after. It doesn't matter. And just by looking at the type, I can determine that. I don't have to look at the implementation of reverse. Just by looking at reverse's type, I know that this law upholds. And also the compiler does as well. The compiler can tell me that. And finally, there's this one here, which is mapping, and then filtering is the same as kind of filtering with the mapping function, and you can get some complicated free theorems from it. So this is something that maybe you didn't come up with, but this is an algebraic law that has to uphold just by the types of the functions. Just by the types, we know that these things are equal. So if we ever need to refactor things, we can use these algebraic laws and say, if I've got this thing, if I ever see someone write that code, I can refactor it to the thing on the right, which I'd much prefer. So that's just something I get for free. So conclusion would be that so equational reasoning lets us kind of substitute through our programs and simplify programs. And so you can see when I did my traverse underscore program, I was able to, what I saw as a simplification, maybe you didn't see it as a simplification, but it lets me reduce this, I had traverse underscore, I had fold right, I had to talk about these things. And when I did the equational reasoning, I didn't have to talk about them anymore. I just had to talk about this one operation, which was the asterisk greater than. So I was able to simplify it in that it removed the traverse underscore, removed the fold right, and left me an operation I need to talk about. Algebraic types is a way of precisely, so we're being precise here, so we're saying that this data type is made up of these different fields, and we're saying that product types is a way of saying it's made up of this field and this field together, whereas a sum type is saying it's made up of this field or possibly this field. So we've got different alternatives at the same time. Algebraic laws is about being able to refactor and simplify our code, but also, importantly, it gives us a lot of code reuse. So because an algebraic law gives rise to an abstraction, we can write functions in terms of that abstraction, and gets us a lot of code reuse. So we exploit that a huge amount on my team. Product-based testing, we exploit a lot as well. All of our tests are product-based tests. Pretty much all of them are product-based tests. So we write down like an algebraic law or some sort of law that our business model represents, like creating a user means that you can find a user, and then we test that it is true. And we don't have to write specific cases. We don't write specific user. We don't write a specific plugin or anything like that. We just generate them and let the code find any problems that we have. And finally, parametricity, where if you exploit polymorphism or if you use polymorphism to its full potential, you'll get directed towards solutions, and also you'll limit possible solutions where you have to look for things. If you are trying to figure out a bug, you can say, I can exclude all of these functions here from possibly being related to that bug at all, which I think is super useful. All right, well, I'm going to be at the Atlassian booth after this, so please feel free to come talk to me. I can talk about this for a long, long time.